is here in person. That's nice. And she will be talking to us about group actions on the circle.
Thanks, and thanks to the organizers for the invitation. It's a delight to be here at MSRI and to be able to speak right at the beginning of this exciting semester. I hope this talk serves as an excuse for you to talk to me about some of the content of it over the next 3 months or however long we're here. 4.5, all right. How he's counting down for fear he might have to leave someday. So I'm going to talk about groups acting on the circle, and I did feel the need to give it a sophisticated sounding subtitle, but you can ignore that if you prefer. Some of the key themes we'll talk about are rigidity and flexibility and moduli spaces of these actions or representations. So let me start by introducing the key players for today. Gamma will be a finitely generated group. Homeo S1 is the group of orientation-preserving homeomorphisms of the circle. And this thing here, which instead of reading hom blah, 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 I'll just call the representation space, is the space of representations or homomorphisms of our group to the group of homeomorphisms of the circle. Right? Equivalently, the space of actions of that group on the circle. So why is this space important? Lots of you here probably think about spaces like this, where instead of homeo as a circle, you've got some Lie group. We have this joke where if you take a big Lie group and put it there, then you're doing higher Teichmuller theory. Well, I just took an infinite dimensional Lie group and put it there, so I'm doing infinitely higher Teichmuller theory. And there are kind of nice ways that the group of homeomorphisms of the circle is like an infinite dimensional Lie group, but I won't go into that very much in this talk. But there is an important geometric or topological interpretation to this space, and that's what I want to focus on. So here's our interpretation. If your group is the fundamental group of some manifold, for instance, some surface, then this representation space is the space of flat circle bundles over your manifold. Well, what is a flat circle bundle? Well, what does it mean to be flat? You have a flat connection, and if you don't like that, it's a bundle with a foliation of the total space that is transverse to the fibers. So here's a picture. I've got a circle bundle over my manifold. To each point, I've attached some circle in some continuous way. And to make this picture easier to draw, I'm going to unroll the circle direction. So now I've got some abstract version of my total space of surface, and then I unround the circle to get something three-dimensional. And to have a foliation transverse to the fibers means that I've covered this in little two-dimensional stripes, transverse, so intersecting transversely each of these fibers. So that's just a little piece of it drawn in there. This is interesting even in the case when your bundle is trivial as a topological bundle. So it is an interesting and rich question even to study flat trivial bundles, in which case you are studying the space of foliations, certain kind of foliations, on a product manifold. So there's a lot kind of richness that comes from this flat bundle thing rather than just topological bundles. Okay. Oh, so how does this correspondence happen? Right? What is this equivalence? Representations and flat bundles. Oh, it's not too hard. It's through the monodromy representation. And I drew pictures on my slide, but I kind of like using the board. So later, after the talk, if you want to look at the slides again, you can do that. But let me draw a board picture, because then we can do it step by step. Okay. So I've got my surface, and I've got my, I've picked some base point, and I want a flat bundle. So I've got some foliation like my previous picture. I want to associate it some representation from the fundamental group of my base to homeomorphisms of the circle, my fiber. And I'll just do this like this. Okay, so I pick some loop, some element of the fundamental group. Maybe it's this one. Went in a direction. There we go. And I'll get a homeomorphism of the fiber over my base point by, well, okay, so here's a point on the fiber. What does this homeomorphism do to that point? Where does it move it on the fiber? Well, I'm just going to lift this loop starting at this point and lift it so it stays in this leaf through that point. Okay, so I've got one sheet of my foliation, and I start following this path along, and maybe the sheet kind of like winds around and comes back over here, so that when I take this loop around, staying on the same sheet, I'll end up over here on my fiber. Exercise check that defines a homeomorphism of the fiber. In particular, the endpoint is independent of what loop I chose, provided it's in the same homotopy class. So now here's the pretty version that you can see later. And it goes back both ways. There's a vice versa. So if I give you a particular representation or homomorphism of a surface group, or the fundamental group of a manifold, to homeomorphisms of the circle, I can build you easily a flat bundle where that representation is the monodrome. So it's a direct encoding. If we want to consider bundles up to the relevant notion of equivalence, then you want to consider representations up to conjugacy. In fact, there's a little bit of a subtle issue here, where we're going to actually think of them up to semi-conjugacy, and that's the right notion for what we want to do. And I will gloss over this a lot. If it's a point that you're interested in, we should talk later. But briefly, you might want to consider two foliations on a space to be basically the same if you could get one from the other by, say, taking a particular leaf, one of these sheets, and just like fattening it up, right, thickening it, replacing it with like leaf across the interval. I didn't really change the topology of what's going on. I just took something that was thin and I thickened it a bit. In the same way, you might consider two actions on the circle the same if you took the orbit of a point and like blew it up to replace all the points in that orbit with tiny little intervals. That operation is performing a semi-conjugacy. You didn't change the dynamics in an essential way. And that equivalence relation where you're allowed to blow up or blow down things is exactly the equivalence that it's reasonable to think about on flat bundles. But if you prefer to just think of conjugacy, just thinking of it like doing a change of coordinates, you won't lose an essential train of thought in this talk. Okay, so what's the basic problem here? I want to understand this space of representations or actions or flat bundles, however you want to think about it. More specifically, you can ask, fix your favorite group gamma. Is this space non-trivial? Right? That's asking if there's non-trivial actions of the group on the circle. Existence question. And maybe you want to be a little bit particular about what you consider non-trivial. Right? Maybe your sophisticated version of non-trivial is you want it to like not factor through a finite quotient. Or maybe even, does there exist a faithful action of your group on the circle? I guess as an even, more refined question along the lines of like, are there interesting examples of representations or flat bundles? You can ask, given a particular like topological bundle, does this bundle admit a flat connection? Is there some representation that does what you want it to do? As a second motivating question, we can try and just describe this space. Right? So some things you might want to look at are, what are its connected components? How many connected components does the space have? Connected components, in this sense, correspond to deformation classes of bundles or actions or representations, as you like. You could also look for isolated points, right? That, in this space, are corresponding to rigid representations, bundles, actions, whatever you want to think of them as. So rigidity comes from isolated point components. And thirdly, and perhaps as an approach to the previous two, you could try and look at how to parameterize this. Maybe it's possible to give some kind of coordinates on this space. That's something we'll talk about a bit. Or even like local coordinates. Anything you could do to get your hands on how to understand this. Okay. So I would like to give you some examples to keep in mind as we approach these questions. And just so you have some kind of library of things to think about, perhaps you've already thought about groups acting on the circle without thinking that you were thinking about them. So here's some familiar examples, at least to advertise that there's a lot of rich geometry going on. Okay, first, take a surface group and put it into PSL2R however you like. You could make this like a Fuchsian thing coming from a hyperbolic structure. It was talked in the other way, but you could also make it some terrible, degenerate, crazy thing. It's, just take a representation in PSL2R. Well, PSL2R acts on the circle by Mobius transformations, so you've just built an action of a surface group on the circle, and we can try and understand, can you deform that in the space of actions? What does this look like? Okay, well, as well as PSL2R sitting inside of there, here's an even simpler subgroup. How about the circle, S1, the rotations? So take a group, abelianize it, and then put it in the group of rotations. That will give you examples. If you start with a free group, then you're free to do whatever you want. Just make the generators act however you like, arbitrary homeomorphisms. If you take any closed set of the circle, that can be the set of fixed points for some homeomorphism. You can build it from there. So you can do whatever you want. And there's lots more sophisticated examples, which perhaps I'll have time to hint at the end, coming from things like if you have a three-manifold with a pseudo-Nosov flow, there's a recipe for building a faithful action of its fundamental group on the circle using the geometry of this flow. So what am I going to talk about today? My goal is really to just give you a taste of some of the tools we use to understand the space of these representation spaces. And, it's kind of a difficult decision. There was a lot of different tools that we bring in, so I tried to, pick a couple things that I have a close connection with and I'm interested in. And so I'm going to give you a narrative, a little bit of a story that will, of course, leave out a lot. But hopefully you'll enjoy my, selected excerpts of a little story. And I've constructed it so that we'll see both, important tools, specific applications of these tools to prove theorems, and then kind of the open questions that are left. So my apologies if I didn't mention you, but I couldn't mention everything that's relevant to this. Okay, so let's start by talking about problem number 3 on my list. Can I give some kind of coordinates? Okay. Maybe this is a good approach to problems 1 and 2. So, coordinates. And as a disclaimer, I have to say this whole perspective I'm going to give is something I originally heard as an idea from Danny Caligari. He's made this analogy before, and it was so good that I came up with it myself later on and assumed I had just made it up, but it was actually his. It had stayed in the back of my mind and percolated for a long time. So, coordinates. But by way of motivation, and because you know, the group of homeomorphisms of the circle is a big group. It's kind of unclear how to parameterize this. I think this problem is too hard. So by way of motivation, we are going to remove this group and replace it with something a little simpler. And if we can parameterize this space, then we'll just try and imitate that strategy to parameterize the other. Okay. Here our equivalence really is like just conjugacy. Or maybe you want to do that fancy thing where you deal, well, if you know what the fancy thing is, instead of just quotienting by conjugacy, you're going to do it, and if not, you won't lose anything. Okay. So this space has a nice set of coordinates that perhaps you're familiar with, and if so, this will be a very quick review. These are trace coordinates. Okay. So let me state some very obvious facts. Trace is a function from SL2R to R. It is conjugation invariant. So this is a good thing if we're trying to understand things up to conjugacy. That's conjugation invariant for you. Oh, whoa, that should be H. So I join the ranks of the great people who have made typos on their slides. And it is not a homomorphism, okay? So that's obvious. But the important thing is we didn't just do something dumb and reduce our group to some very much simpler group. This has the chance to capture more information. And here's the theorem. The theorem says this captures information. If I take two representations of some finally generated group to SL2R, and I know that the trace of the image of every element agrees, then these are the same representation. They're conjugate. There's a tiny little y. If I really want them to be conjugate, I need some non-degeneracy assumption, which here basically comes down to not being upper triangular. The problem is, right, the identity matrix and something that's 1, T, 0, 1 have the same trace, but they're not conjugate. Okay, so you either solve that problem by taking a funky quotient or making some non-degeneracy assumption. So I took something away. I made this extra hypothesis, but I'm going to give you something back. You actually only need to look at elements in some finite set. So really you've got coordinates on this space that, make it finite dimensional. So far, so good? Okay, let's do this with homeomorphisms of the circle. Okay, so what do I want? I want a trace. I want a conjugation invariant function from, say, homeomorphisms of the circle to R. Well, Poincaré came back from, he heard my plea and went, I'm in my time machine and solved this problem for me a long time ago. Here's his rotation number that solves this problem. So you have the circle, and what my picture is the universal cover of the circle, which is that line. Given a homeomorphism of the circle, I can lift it to a homeomorphism of the line. Right? So if I take a lift, it's going to commute with the covering transformation, which is translation by 1. So that's why I've written F tilde, the lift, is in homeo ZR. That's the homeomorphisms of the line that commute with integer translation. The translation number of this lift is a real number that captures how far the lift translates points to the right on average. Okay, so how am I going to do that, capture this? I'm going to pick a point. I picked 0. I'm going to iterate. I'm going to hit that point with my homeomorphism over and over and over again and divide by the number of times I applied it. So I'm getting the average translation distance and take the limit as n goes to infinity of this. Okay, so average distance overall. Theorem of Poincaré, this is well defined. And in fact, it didn't matter what you called 0. You could have picked any point. You'd get the same answer. It is conjugation invariant. it is not a homomorphism. So this, we're capturing some information. We have a hope that this will give us good coordinates. That's a nice exercise you can do. Give me examples, draw me a picture of two lifts which both, say, have translation number 0. Say they fix a point, but where their product has translation number 1. So there's something that's eventually translated 1 over. That's a fun thing to play around with if you haven't thought about this before. Okay, so we're looking like we're in business, except, oops, what happened? What went wrong? I was looking for a conjugation invariant function from the group of homeomorphisms of the circle. And here I made this choice, right? I said choose a lift. This translation number depends on the lift that you chose. So we have to, we're not quite there yet. Okay. But there's two ways to solve this problem. One is an obvious way. You look at it mod z. That does not depend on the lift. So do the same definition and say mod z. Then that takes care of different lifts differ by some integer translation. So that's the original definition of the point k rotation number, which is capturing how much you rotate the circle around. But there's another solution. Here's a more sophisticated thing you can do. I'm gonna. That was our how mod z is going to be this function. It goes to r mod z. Okay. Here is our more sophisticated answer. I'm going to find something that takes as input two homeomorphisms of the circle. And as output will give me some real number that does not depend on the lifts. If I choose different lifts, maybe a quick exercise you can do to check to see that this difference that I'm taking does not depend on the lifts I chose. Integer translations will just kind of commute and fall over there, out of there. So my first solution, looking mod z, it does not give coordinates. It's not a good candidate for replacing trace, unfortunately. Okay. So here's an example to convince you. You take a surface group, and you put it into PSL2R in the Fuchsian way. So here's a picture of two, say, generators of the group acting. They're acting by hyperbolic, isometries of the universal cover of your surface. So on the circle, they're doing, they have two fixed points each. And they're doing this kind of source sink dynamics. Familiar picture? Well, the fact that they have fixed points when they act on the circle means that the rotation number, translation number, this average rotation is 0. They have a fixed point. They're not rotating that point at all. So in fact, for a Fuchsian representation, something we like to think of as highly non-trivial, discrete, faithful, doing important things, this tau mod z is 0 across the board, same as the trivial representation. So this is not distinguishing it from the trivial representation, so not good coordinates. So instead, perhaps, let's take a closer look at C. Okay. So this function C is actually, it's a cocycle. It satisfies the cocycle condition, its boundary in the sense of that inhomogeneous bounded cohomology thing, the formula that Alessandra wrote down in her talk, its boundary is 0. Okay. So I can think of it as an element of bounded cohomology of this group as a discrete group with real coefficients. And it's also not hard to see that the way I've defined it forces it to be bounded. I think its maximum value is certainly less than 2. So bounded cohomology has found itself another use. And I guess here's an aside for the experts. If you want to know what's really going on, that translation number is a quasimorphism, not a homomorphism, and this cocycle is its boundary in the usual boundary, in the usual way that quasimorphisms give you bounded cohomology. This, we heard the name of it before, it is the real bounded Euler class. if I take a representation of my group to the group of homeomorphisms of the circle, some action of the group on the circle, I can use this to pull back the Euler class to an element of bounded cohomology of my group. And here is the miracle theorem of Gis and Matsumoto. It says that this representation, this element of my representation space, is determined by this Euler class. Okay? This thing that I built out of translation numbers. And one more thing. You would need a little bit more data, which is to look at tau mod z on a system of generators. Just so on finitely many elements. So translation numbers, thought of this way, capture the representation completely. This is in the sense in which I want to think of them as giving coordinates on this space. This perspective has proved to be incredibly fruitful. So I'm now going to overwhelm you with results that I claim are achieved by thinking about actions on the circle in exactly this way, thinking about translation numbers. And the first is the Milnor-Wood inequality, in the sense of it being maybe some kind of existence result. Now, Alessandra gave us a formulation of Milnor-Wood inequality for PU11. That's sort of what Milnor did as a contribution to this. He was thinking about surface groups into SL2R, or principal SL2R or PU11 bundles. Okay. Wood had this brilliant insight that secretly what Milnor was thinking about was this cocycle in terms of translation numbers, which applies to the group of homeomorphisms of the circle. And he managed to prove the same thing for general circle bundles. So the Milnor-Wood inequality states that a circle bundle over a surface admits a flat connection. So it comes from one of these monodromy rep building things. If and only if the Euler number of this bundle is less than or equal to the Euler characteristic of the surface in absolute value. So that Euler number is something that comes from a characteristic class of the bundle as a topological bundle. And this is saying when it has a flat connection, when this bundle could have been a flat bundle. And we saw a different proof of the special case, but Wood's proof really does use look at how far points are being translated along a line. It's this translation number perspective. It's quite beautiful. Okay, another result. So we have some kind of existence result, existence of a flat connection. These are going roughly in chronological order, I think, of my selection of favorite things. So my next favorite is this rigidity result of Matsumoto. It says that a representation or a flat bundle has maximal Euler number, so equal to the Euler characteristic of the surface, if and only if it looks like a Fuchsian representation. It looks like discrete faithful into PSL2R. It looks like some point in Teichmuller space. So, you probably think of Teichmuller space as a whole space of Fuchsian representations, but when you allow conjugacy and homeomorphisms of the circle, they're all the same. They're all conjugate. They all, you draw that picture of the universe covered and what things are doing. Well, the action on the circle is the same dynamically. It is the same up to conjugacy and homeo, S1. Right? So what Matsumoto's theorem says is, in fact, Goldman found that for representations into PSL2R, having maximal Euler number gives you this one connected component, the Teichmuller component. Matsumoto says that for representations into the space of homeomorphisms of the circle, maximal Euler number gives you one connected component, the semi-conjugacy class of these Fuchsian representations. It's a very strong rigidity result. Surprising, I think. Danny Caligari has done some thinking about this in this terms. I've mentioned that, these trace coordinate analogy came from him. he produced rigidity examples for other groups. Right? Building on Matsumoto's idea, he can construct explicit groups that, like, only act on the circle in one non-trivial way. So this is from a paper called Dynamical Forcing, where he shows how you get particular rotation or translation numbers for elements. And Caligari and Walker, in a quite recent paper, really studied kind of deeply these trace coordinates. They were able to draw pictures of what I can best describe as slices of this representation space in translation number coordinates, where your group is a free group. So let me show you kind of what these pictures look like to say what I mean. Here are some of their pictures. And what is this telling you? This picture is a three-dimensional plot. It's a graph. And it's comparing the translation numbers of two generators of my free group with the translation number of some word in the generators. Their product, or this one, I think, if I have A and B, this is like A, B, I think. That one looks like a commutator. So this is giving you a little, slice of this representation variety in in translation number coordinates. What does it look like? And it looks a little crazy. There's something kind of deep and difficult going on. The paper where they draw these pictures really, developed some kind of, how do they draw this picture? They got a computer do it, so they got some kind of algorithm to tell you what are the possible values of translation numbers of a product. These pictures are telling you how far away it is from being a homomorphism. If translation number was a homomorphism, they would look like an even slope, just a plane. Okay. So using this paper, I was able to get some nice further rigidity results and classify more connected components of this representation space. In particular, I found some new rigid representations of a surface group into homeomorphisms of the circle. So these are kind of, one of the only examples I know where you get rigidity without some kind of maximality. Maximality implies rigidity is this big theme in higher Euler theory. But here are examples with non-maximal Euler number that are still completely rigid. Their deformations are all trivial. They're all just semi-conjugate back to themselves globally. But these are still kind of nice and geometric. I can draw you a picture right now quickly of what they look like. Okay? So you take your favorite Fuchsian guy, and this gives me an action of a surface group on the circle. And I want to build a different action of a surface group on a circle. So I'm going to build you a new circle. I'm going to unwind my original circle k times and get a k-fold cover, which conveniently is still the circle. And then you just lift the action of your group to an action on the circle. So, this red guy has 2 fixed points and has source sink dynamics. Its lift to this 4-fold cover in the picture will now have 8 fixed points with, the arrows are indicating what direction points are moving along. You can't always do this, but we know the obstruction to doing it comes from this Euler class. So in many cases you can. And these examples that you build this way, for any lift you take, gives a rigid representation. Can't be deformed, even if however you want to fuss with it in the space of representations to homeomorphisms of the circle. So from this gives you identification or classification of more connected components of this space. But, there's still a lot of open questions. Right? I found some more connected components, more than that are given, by just looking at Milner Wood or what we knew so far. But we still do not know whether this space has finitely many or infinitely many connected components. If I replace homeo of S to the circle with some like nice finite dimensional standard Lie group, putting, GLNR or something in there, then you know kind of for free from algebraic geometry that this thing ends up being a variety and so can only have finitely many connected components, general fact. Here, totally unknown. And people have tried to get me to say one way or the other, and I refuse to say finitely or infinitely. I actually have no idea. I actually have no idea. These days I say finitely, but I won't bet you more than $5. Yeah. Whoa, there we go, sorry. It all happened all at once. Another open question, which I will put money on, is are there more examples of rigid representations, new rigidity phenomena that hasn't been discovered? Right? So far I'm talking only about surface groups. Already we have a bunch of work to do and unanswered questions. This, I'm going to bet no. If you find one, I will be very excited and surprised. So I'm willing to sort of go out there and say, like, hey, these examples that I constructed, they are all the rigid ones. And my reasoning is the following. In some sense, it's a complete list of everything geometric. So I'll call a representation geometric if its image is in some Lie subgroup of homeo of the circle and is discrete and faithful inside of there. Okay? I found them all. They come from that list. They're all rigid. Okay, done. If you find something else, I'll be fascinated. Maybe further good evidence for this is Matsumoto, the one from the rigidity theorem before, tried to kind of redo this, and he got exactly the same answer. So there's a paper of his that just went on the archive like about a month ago that studies rigidity and components of this representation space from a different perspective, a more dynamical perspective instead of this translation number thing. And lo and behold, he recovers the exact same result that these examples that I found are also examples that he found of rigid representations. So we've got, two people now saying that like these are the ones we can find. Maybe that's it. Here is a very important question of a different flavor, which is the space of foliated products connected? So I take S1 across the surface. That is, as a topological space, very, simple to think about. And I try and understand all of the foliations on this space, all of the ways of striping it in a way transverse to that fiber direction. All the possible of choices of a horizontal to compare with the vertical fiber. Is that space connected? Not known. Equivalently, these are the circle bundles with Euler number 0, if you prefer to think of it that way. Is that a connected space? Flat bundle. Not known. I think that's kind of shocking. We just don't know. And finally, here's something that's maybe even more surprising. Is this space locally connected? Okay, so it could be extremely messy. It probably is. It probably is messy. It's probably not locally connected. That is a difficult question. If you place homeo by diff, this is a difficult question for other reasons. Both of these are of interest to people in dynamics. And finally, of course, you can think about groups other than the fundamental group of a surface. Replace this with another gamma. Maybe you like 3-manifold groups better. Try and answer the same question. There's kind of a nice analogy here that I'd like to make before we move on to a different perspective. Why this surface groups case? Well, here's my optimistic fairy tale story. The Milnor-Wood inequality that we told you about, Milnor kind of had this great insight and proved it for representations, effectively representations of a surface group into PSL2R. And then Wood came along and looked at it and was like, hey, I see what's really going on there. This works for homeomorphisms of the circle if you spin it the right way. Well, Bill Goldman, a while ago, classified the connected components of this space where you replace homeo of the circle with PSL2R. complete classification of connected components. We need to find the person who will like spin this the right way and figure out the answer for homeomorphisms of the circle. Okay, so, challenge to us all. Okay, but considering there's so many open questions so far, maybe we need a bigger arsenal of tools to attack them, so I'm going to switch gears for a minute and give you a different approach to these problems, one that is also quite dear to my heart. So, switching gears, here's another perspective. And this one, so far, has been good for kind of existence questions. Are there interesting examples of actions of groups? So, here's a question you might want to ask, one from our list. Does my group gamma, my favorite group, act non-trivially, faithfully, interestingly, however you want, on the circle? Well, seems intimidating, but if I replace the circle with the line, then there is a beautiful algebraic characterization of which groups act and don't act. Here's the theorem. My group gamma acts faithfully on the line by homeomorphisms. There's an injective homomorphism from gamma to the group of orientation-preserving homeomorphisms of the line. If and only if gamma satisfies this algebraic condition called being left orderable. What does left orderable mean? It means there is a total order on your group that is invariant under left multiplication. So A is less than B if and only if GA less than GB for all A, B, G in your group. Example? How about R as an additive group with the usual order and addition? So check it in your head. Addition is invariant under left addition, I guess. That's our canonical space, and turns out that the whole group of homeomorphisms of the line is also left orderable in this sense. And for countable groups, in particular for finitely generated groups, gamma, there's an exact equivalence like this. So the way I've written down this exists a total order is only actually one way to define left orderability. There are many other equivalent definitions that are nice to work with. It's a remarkably simple thing to check. In fact, there's even conditions that are sort of finitely checkable. You can ask a computer, is my group left orderable? And if it's not, it will tell you that in finite time. Okay. This perspective, I promised lots of applications, has been quite fruitful. Here is one. Theorem of Dave-Woody-Morse, which says that if I take a finite index subgroup of SLNZ, and at least 3, then this group has no faithful actions on the circle. Using left orderability, how? Here's the idea of the proof. By a theorem of Gis, which also has been proved later by Berger-Monod, if I take such a group and it acts on the circle, then up to finite index, there will be a further finite index subgroup of it that fixes a point. It's a global fixed point. So they show there's some periodic orbit. Past the finite index, you get a fixed point. So that point I've drawn on the circle is fixed by all elements of my group. Haha. Circle without that point, fixing that point, that gives me an action on the line. I found a line secretly in there. And then you show using this kind of nice algebraic condition that such a group is not left orderable. So it can't act on the line faithfully. Okay, well, so I left out all the details, but that's the strategy. There are many generalizations of this known, but it is open whether I take just any lattice you want, any lattice, the general case. Does this have a faithful action on the circle? Or, we expect no. Do all actions factor through some finite group? This is still open, although there's lots of partial related results known. Dave Morris has a nice survey article that lists, from 3 years ago that lists the state of the art at the time. Okay, well, seeing as left orderability didn't quite get at the full generality. Let's go back to our original question. I got distracted. I went on a digression of what this is useful for. I wanted a algebraic condition, maybe like this one, that told you when a group acts faithfully on the circle, not the line, the circle. So let's try and do the same thing for the circle instead of the line. Okay, so here's what I want. I want a theorem that says gamma acts faithfully on the circle if and only if it is circularly orderable. Okay, and I don't know what that means, but as an example, I better have the circle. Right, this analogy is going to hold. So let's figure out how points are ordered on the circle. That will be our definition of circularly orderable, and then we'll try and prove this theorem. So, circularly orderable. Got a couple points on the circle, and I want to decide if one is less than the other. So let's say x is less than y if you move counterclockwise to get from x to y. But of course that's nonsense, right? Because you could go both ways. Okay, so that's not going to work. So I'm going to take a third point, and now the order of a triple does make sense. That x to y to z is counterclockwise. Or better, that this triple is positively oriented, having fixed an orientation on the circle. And you'll notice that this orientation, this idea of orientation, is invariant under left multiplication in S1. So our setup looks good. So I'm going to define a circular order to imitate this. It's a circular order on a group is some function from triples in my group to plus minus 1 or 0, where I'll send repetition to 0 and a triple to its quote-unquote orientation. That would tell me how points are ordered on the circle. And I want some kind of compatibility condition on 4 tuples. So if you look at your points in the circle, if I give you 4 of them, arrange them however you like, you cannot, if you look at the orientation of triples one by one, there's some relations in between some and the others. So if I tell you, the orientation of xyz, yzw, and wxz, then the last one you're going to have to figure out from the ones I've given you. Not everything works. So you can figure out what that compatibility condition is that gives you for the circle, and then I'll just take that same thing and say that's what I need on this function for my group. Okay. So circular order from one perspective. And the problem is that, well, maybe the right thing is, the good news is that this captures a lot of information about groups and whether it acts on the circle. So that theorem that I showed you, the one that we wanted, magic theorem, acts faithfully on the circle if and only if you have a circular order in this sense, is true. In fact, a circular order even gives you a particular way of constructing an action on the circle that's faithful. This is not hard to do. It's even easier to do for the line, that theorem, but I don't have a lot of time, so this is maybe a fun one for afterwards with a chalkboard. Okay, so this theorem works, but the bad news is maybe that it's not new, because secretly we just recovered something that we found before. So this new perspective, circular orders, is actually just a new perspective on our old perspective. And here is the miracle that ties it all together. That compatibility condition on what 4 tuples are, what orders are allowed if you have 4 points, is the cocycle condition from homogeneous cohomology. Its co-boundary should be 0. It ends up being exactly the algebraic thing you need to satisfy. So I can think of this order thing as a cocycle, as a homogeneous cocycle, an element of second-bounded cohomology. Right. This was the picture that Alessandra was drawing in her talk with points on the circle. Our theorem from before, that if I have a circular order, then that lets me build an action of my group on the circle that's faithful, right? If I take that action that I get, then here's the theorem or observation that I'm not sure actually who it's due to originally, but I've seen it in Thurston and Gies, and it's now very well known. It's that you can do a little computation, and that order cocycle on my group that comes from a circular order on the group is twice the pullback of my C cocycle from before that we saw. Both of them elements of second bounded cohomology. Okay. So on the one hand, this proves that the order cocycle is what you should be looking at, because circular order here tells you this or bounded order class cocycle that was supposed to tell us everything about the group action. So either you've done nothing new, I'm just looking at the Euler class again, or you've done something really good, which is to understand it in a different way. Right? Perhaps you can answer more questions by trying to understand all the possible circular orders on a group. There's reasonable ways to topologize the space of circular orders or the space of left orders on a group, and yet it's not very well understood what the space looks like. Okay. And in fact, this correspondence, this if and only if thing, is also not quite as nice as you'd like it to be. An order gives me a canonical way to get a group action on the circle, and a group action on the circle induces a circular order on my group, but it's not a one-to-one correspondence. Some actions on the circle don't, the ones I get going this way are all of a very particular form. But nonetheless, I think this perspective, it's been kind of underused and might be very fruitful. Okay, so we're nearing the end. It's time for me to assign you some homework. Your first problem is to describe the actions of your favorite group on the circle. Okay, so I've talked a lot about surface groups. I've mentioned other interesting geometric examples, but here is a slightly longer list. We mentioned lattices and semi-simple Lie groups. We had this question about higher rank, where there's still open questions if there exist faithful actions. And in rank 1, there are faithful actions, like think of a surface group in PSL2R. And these are pretty much classified by theorem originally of Gies. So those are good things to think about. But perhaps you're not a lattice person. Perhaps you like 3 manifolds. In which case, as I mentioned very briefly before, there are actually many ways that some geometry of a 3-manifold gives you a faithful or otherwise nice geometric action of its fundamental group on the circle. So a foliation of a particular type, our covered nice-looking foliation, will give you such. And also flows let you build this. These fall under this term called universal circles. If you have a foliation on your manifold or the stable foliation of a NASA flow, you try and identify sort of the boundary of the leaves with a circle in some kind of nice compatible way. And this ends up giving you an action of the fundamental group on the universal circle, this circle at infinity. This introduced by Thurston and pursued by Caligari and Dunfield. The mapping class group of a surface with a marked point, maybe you like mapping class groups, acts on the circle, again by looking out to infinity at the universal cover. You can do a similar construction for the mapping class group of a surface with boundary components. We talked about surface groups. You get different looking actions if I'm thinking not of a hyperbolic surface, but like take some negatively curved metric and look at how things look at infinity. And there's lots more. I've given you some references. The talk slides have a bibliography to them at the end, which you can peruse and click through. I tried to be as good as possible. So that's your homework. And maybe I should say what I'm not going to say, which I'm not going to say, is that the talk has an epilogue. There's a lot of other things that I wanted to throw in here, but of course can't. Okay, so as a teaser, let me tell you what the epilogue looks like. It looks something like this. It's very long. It's what I didn't say. Okay, but, oh, not this one. Come back. Where's my talk? Should have prepared this better. Okay, so that's there for you to peruse at your leisure if you want. Things I didn't say, like questions of regularity. Replace homeo with diffeomorphisms, or CR diffeomorphisms, or PSL2R, or the group of quasi-symmetric homeomorphisms of the circle. This changes these representation spaces a bunch. You start looking at smooth flat bundles instead of flat bundles. Dynamicists are interested in these kinds of questions. Some of these questions that we want to answer, like this Zimmer program thing I talked about, higher rank lattices, do they act on the circle? Answered if you want your action to be by smooth diffeomorphisms. So regularity changes things a lot. That's a thing you can look into. I didn't talk about other approaches to bounded cohomology, which we saw a little bit in Alessandra's talk that end up giving us a lot here. And another thing I didn't talk about was, well, I talked a lot about gamma. I talked a lot about our group, it being left orderable, it being having these cocycles on it. I didn't talk a lot about the group of homeomorphisms of the circle as a group. What does it look like? I hinted it should be an infinite dimensional Lie group. Oh, well, what's its Lie algebra? How can we understand this group as both a topological group, a topological space, and as an algebraic structure, and how its algebra relates to its topology, which is something I've thought a lot about recently, and there's some very surprising things. So there's lots more that I didn't say, but I'm not going to say it, so I will go back to your homework, and I'm just out of time, so I'll end there. Thanks.